Okay, so welcome everyone back to Math 140 Business. This is my first lecture of week 9. I think, I don't even know what lecture number it is, but it's whatever the next one is. And we are starting with chapter 20. Someone said not business. My Math 140 science, not business. Thank you. 140 SCI. Thank you. And we are continuing with chapter 20, which is called Inference about a population mean. Oh, I remember now. Yes, I remember now. Inference about a population mean. And we started the first section talking about conditions for when you're allowed to use the population, the sample, to make inferences about the population. In particular, it has to come from an SRS. It has to come from a normal distribution, or at least something that kind of looks normal. So far, we've had two possibilities. Case 1, sigma was known. And in the case where sigma is known, our confidence interval was x bar plus or minus z star sigma over the square root of n. That was the confidence interval that our calculator does for us in the situations when sigma is known. And situation number 2, which we did last time, was sigma unknown. And can someone remind me what was the formula for the confidence interval in the case when we do not know sigma? Anyone recall the changes that we made in the situation when we do not know sigma?
It was x bar minus t star times s divided by square root of n. And then the same thing with
plus. Right, exactly. So we make two changes. The first change is the obvious one. If you don't know sigma, you can't use it. So what do? If you want to have a formula that normally has sigma, but you don't know it? So the answer is you approximate it. And what's the best thing to approximate the population standard deviation with is the sample standard deviation. So you replace sigma with S. The other change is we replace Z with the S is the sample standard deviation. So it's, if you remember from chapter 1 or 2 or 3, whatever it was, the formula for the standard deviation of the sample. You calculate the mean, you calculate the deviations, you square them, you add them, you divide by n minus 1, and then you take the square roots. That whole formula gives you the sample standard deviation, that is S. At the end of the day, if you're going to use your calculator, it'll give it to you either way. You don't have to worry about it. In terms of the test, it still hasn't been officially decided. As of now, it's still Tuesday. We will talk about it a little bit more on Thursday, but for now, plan ahead for it being on Tuesday. So these are the two confidence intervals that we have so far. We have the one where we know sigma, and therefore we use Z star and sigma. Can you write in the formula to find this? Oh, well, S equals the square root of the sum of the xi minus x bar squared over n minus 1. That's an old formula from earlier in the semester. You will not need to do that by hands for any sample size more than like 3 or 4. It's just unnecessary busy work for absolutely no reason. Okay, but at this time, the next question is, how do I find T star versus Z star? And the answer again is we're going to use tables, just like we used Z star tables. There are T star tables, and I believe, if I remember correctly, the last thing we did last time was show you the table of T star. And we saw that in order to use T to find T star, we must know how many degrees of freedom we have for one sample of size n. The number of degrees of freedom is equal to n minus 1. And if you use a table to find T star and the exact number of degrees of freedom is not given, always err on the side of fewer degrees of freedom. And what I mean by that, I will demonstrate after everyone writes it down. I'll give you guys a couple seconds. Computer died. I'm sorry. We should have a funeral now. What do you think? No? All right, well. So I'm going to stop sharing and I will share my computer screen. All right. So we can let's do an example of using T. How about this one? Just happens to be the one in front of me. She sounds tall. Presented with recordings of a pair of people of the same sex speaking the same phrase, can a listener determine which speaker is taller simply from the sound of the voice? 24 young adults at Washington University listened to 100 pairs of speakers, and within each pair were asked to indicate which of the two speakers was taller. Here are the number correct out of 100 for each of the 24 participants. Assume that these young adults can be regarded as an SRS. Use a 95% confidence interval to estimate the mean number correct in the population of all young adults in the United States. So what we have here is 24 pieces of data. We would like to calculate a confidence interval, 95% confidence interval, for the true average of all young adults in the United States, even though our sample is just 24 of them from a specific university. But presumably, unless that university is, the best in the world at voice height recognition, and students who go there have a leg up on the rest of the population, there's no reason to assume that these 24 are not just regular, good old-fashioned random 24 people. And we're assuming that for the SRS. And we want to create a confidence interval, which we know is going to be the form X bar plus or minus T star S over the square root of n. Now, which of these four quantities, X bar, T star, S, and the square root of n, is the simplest to calculate for this particular example? X bar, T star, S, the square root of n. One of those is really, really easy. And the answer is n. What is n in this example? It's just 24, the number of people. That was really easy because they gave it to me. What's the next easiest of these four quantities, although it's not as easy as n, which was essentially no work whatsoever. What will be the next easiest of these four quantities? Anyone? X bar, good. How do I find X bar if I really wanted to? How would I go ahead and find X bar? Plug points in tables. I wouldn't need a table to get X bar. Here's all 24 points. Even a graphing calculator. I mean, yes, a calculator can do it. Statistics, okay, statistics. Followed by.
You go to descriptive.
Descriptive, followed by.
You click the, yeah.
Okay, so n is 24. X bar is 62.17 and S is 5.806. But we don't have T star, do we? Not from here, at least. What if I make a confidence interval? Where do I find confidence intervals?
You go to statistics and isn't it like Z or Z?
Well, it would only be Z
Z.
if I knew sigma.
Oh,
Since I don't know sigma, I do T. Now, is it a one sample, a two sample, or a paired T test? Spoiler alert, we haven't learned any of these two yet, which means it should be a one sample plus it's just one sample. So, and then we're going to do a confidence interval, and they wanted a 95% confidence interval. And if we calculate it, oh, we got to tell us what to calculate, correct? Okay. And if we calculate it, there is the confidence interval. And notice how it tells us the mean, which we need, and which we need. It doesn't give us the standard deviation. It gives us a standard error. And that's a good thing to know. Standard error is already including the square root of n. So the standard error is S over the square root of n. So if the problem said, hey, what is the standard deviation? I would say, oh, well, 1.185 is the standard deviation over the square root of n, the square root of 24, and use that to calculate S. But they don't directly give me S. But that's okay, because they give me what's most important, which is the actual confidence interval. Now, somebody interpret this confidence interval for me, please. In the context of this problem, what does that confidence interval mean? In the context of this problem. It means the true percentage of people, young adults, who can directly or correctly predict the taller of a pair of people based upon the sound of their voice. We are 95% confident that that true value is between 59.71 and 64.62. Is it definitely between these numbers? No. But we're 95% confident that it is. What does that mean that we're 95% confident that it is? What it really means is that if you were to create lots and lots and lots and lots of confidence intervals, 95% of them would capture the true value. So we interpret that to mean that there's a 95% chance that this particular confidence interval captures the true value. But technically that's not correct. It's just how we usually think of it. There's a 95% chance that we caught it. It's okay to think of it that way, but it's not technically correct. Technically, 95% of all confidence intervals of size 24 will catch the true value. That's what it means that we are 95% confident. But all that notwithstanding, the question was, I mean, this was the answer to the question, but what I also want you to think about, what I also want to do is to go to a T table and show you tables. T distribution. So if you look at this table, you will see that there's different levels of confidence, which is one of the things that we need. We like confidence and we like degrees of freedom. Now, if there's 7 degrees of freedom, then there's no question. This is the row that we're looking at. If there's 18 degrees of freedom, no question. This is the row that we're going to look at. What if there's 72 degrees of freedom? If there's 72 degrees of freedom and I want to use this table, I mean, if I wanted to be really accurate, I wouldn't use a table. I'd use Crunch It. I'd use my calculator. I'd use something that's more exact. But if I'm stuck with this table, if this is all I have, and I want to do 72 degrees of freedom at whatever confidence level, which row do I look at?
$60.
Yes, you always err on the side of fewer degrees of freedom. Because if you look at those values, they get bigger as I move up a column. And a bigger T star makes a wider confidence interval. And the wider the confidence interval, the more likely it is that we catch it. So we err on the side of caution. By making a fewer degrees of freedom, we make a wider confidence interval. So to claim I'm 95% confident that I caught it, if it's wider than it has to be, I'm even more confident. So I'm certainly within my rights to claim 95% confidence. If I went down and it got smaller, now I'd be lying. So when it push comes to shove, when it comes to picking degrees of freedom, use your calculator. And in fact, let's do that right now on the TI-84 just to do this as well. We did it on Crunch It, but let's now go to the TI-84 calculator. And we're going to go back to Crunch It here, only because I don't want to have to input the lists into my calculator. So where do you think we go?
Stats and then tests.
Stats and then tests. Okay, which one?
Two.
It is a T. Well, we're not doing a test here. We're doing a test. We're doing a T interval, correct?
8.
So 8 T interval. Are we gonna do data or are we gonna do stats? Stats, because I don't want to input the data, although I could, I have it. What am I going to put as X bar?
62.17.
62.17. What am I going to put as S?
Would it be the 1.185?
Well, remember, 1.185 is not S.
Do we have to calculate it again? Because I don't think it's there.
We do have to calculate it. The question is, what's the calculation? 5.80, I have 5.805, not 5.806. What I actually put in, just to show you, is this. I actually wrote 1.185 times the square root of 24. Because we know that 1.185 is the standard is S over the square root of 24. So if I multiply both sides, and then I hit enter, and amazingly, it gives it to me like this. It doesn't leave it in that 1.185 square root of 24 form. It actually calculates it for me. It gives me 5.8052906903962. Lots of decimals, how nice. And what is N?
24.
24. And what's my confidence level?
95.
95%. So what does the calculator give me?
$59.719 and 64.62.
Which is basically what the computer gave me. Right? Now, if I rounded, it should be 59.72, and they have 59.71. And the only thing I can think of, which seems like a pretty good answer, is that the 62.17 that we're using for our X bar and the 1.185 that we're using for S, those are only approximations. They rounded those and we're using them as exact values. As such, our answer is going to be slightly off, but certainly within, you know, close enough to give us an acceptable value. Does that make sense though? Any questions? Yeah?
No.
Okay,
I have a question, actually.
go ahead.
We're supposed to be on T interval, right?
Yes.
Because I can't see the answer like you're saying. For some reason, mine says 61 to
No,
62.
your S is wrong. S is now 1.185.
For S, when I input it like in the parentheses, it automatically becomes 1.185.
Do me a favor, put in what you had there, and then before you hit enter, show it to me.
What I had before. I had it.
No, for your SX. You should have 1.185 times the square root of 24.
Oh yeah, I just put that, and then when I went down to calculate, it automatically.
No, I'm saying
deleted it again.
don't move out of that spot. Keep it as 1.185 times the square root of 24 before leaving that spot.
Okay. So that.
Where's this 5.806 coming from?
Aren't you supposed to multiply, not divide?
No. S is equal to 1.185 times the square root of 24. What you should be writing is, you don't have 5.805 yet. How do you know that number? You've already done some calculation. That's how you're getting it. You don't have that number.
I got that calculation from what we did before.
Right, I understand, but
Yeah.
we have to act like we haven't done that. What we have here, 1.185 is equal to the unknown S over the square root of 24. So how would I solve mathematically for the unknown S?
Multiply by radical 24.
Multiply what by radical 24?
Both sides.
Okay, so what would I get? S equals what?
Oh, should I do
No, just read it. S equals what?
1.185 divided by, multiplied by radical 24.
And that's what you put in for S.
Okay.
right? That you just solve for S. Put it into your calculator, 1.185 times the square root of 24. That's what you put in for S. That's what S is.
Okay.
And when you leave it, what does it turn it into?
1.185. Why am I getting the same answer? So
No. Show me again. Show me what you're writing. For S, it should be 1.185 times the square root of 24.
I have this.
Okay, now move your cursor down one and show me. See, look at it now. 5.805, that's it.
And then when I press calculate, it shows me this again. Am I not supposed to
No.
get the answer after I press enter? I'm not sure.
It should. Okay, go back there again.
Okay. I pressed it too soon. I see now.
So we're all good now.
Yeah.
Okay.
Thank you.
Mazel tov. Okay. So let's keep going then. Okay. Okay. All right, so that takes us to the end of the confidence interval portion of this chapter.
What's the
So what-
second to last word that you wrote on there?
Fewer
Oh, thank you.
of fewer degrees of freedom. Writing with this thing, this Apple Pencil. If I go slow, I can write very neatly. But I tend to write fast, and when I write fast, it's hard to maintain that. Penmanship. Okay, so we have two tests, two confidence intervals so far. We have the confidence interval where I know sigma. What's the word next to always? Error, ERR. That was written pretty neatly. That's what you're talking about? Error? You know, to err is human. Make a mistake.
Professor?
Okay, to err on the side of caution. Okay,
Professor?
yes.
Is this definition in the textbook
Definition of what?
of this, right here, the to find T star, whatever?
I mean, yeah, I'm sure they say it somewhere in the textbook, not in those words.
Okay, I just wanted to see another way it's written.
Oh, you don't like the way I'm doing it, huh? I see.
No,
how it is.
it's not that.
No, it's okay. I get it. I get it. No,
No.
okay. It's fine. I mean, I haven't been told to like that in days, so that's good. You're gonna find it on the section 20.3 in the box. It says the one sample T confidence interval. In fact, you know what? I'll even share my screen, because I think the way I wrote it is even better than the books, but that's what they have in the box. They say at the bottom, where T star is the critical value for the Tn-1 density curve with areas seen between negative T star and T star. That's how they define T star. Okay.
Got it.
All right. Okay. Oh, I gotta unshare this. Okay. So we done confidence intervals now. When you know sigma, when you don't know sigma. What is the other half of the coin? Those are the tests. So just like we're gonna have two confidence interval situations, we're gonna have two situations when it comes to tests. And the first one is when sigma is known. When sigma is known, let's remind ourselves, what was the format for doing a hypothesis test? You had a null hypothesis where mu had some specific value, mu equals mu naught. This here is a specific given assumed value. And then we also had the null hypothesis where mu is either greater than mu naught, or mu is less than mu naught, or mu is just straight up not equal to mu naught. Those are the three possibilities. What is mu, by the way, in these situations? Mu naught is a specific given assumed value, but what is mu?
Isn't it the mean?
It's the true value, right? The true population mean. Mu naught is what we think it is. We're hypothesizing that the true value is this number. Or we say, no, it's not that number. It's more than that number. It's less than that number. It's equal to that number. And then what we do is we have an alternative hypothesis where we say that, no, mu is bigger than it, mu is less than it, mu is not equal to it. And then we perform our test. And then we test, right? And then we test. What does that mean, we test? We take a sample of size n. Take a sample of size n. And then we do what with that sample of size n? How do we test whether or not the null hypothesis is correct, or whether we reject it or we don't reject it? How do we do a test? We take a sample of size n and do what with it? Who remembers? How do we test? Anyone? We calculate the what?
Is it the MOE?
The MOE.
And
Oh, margin
margin
of
of-
error. No, margin of error is about confidence intervals. The margin of error is just these. These are the margin of errors. The plus or minus, those are the margin of errors. Margin of error doesn't play a role in hypothesis testing. We calculate the p-value. Which is the probability of being more extreme than the sample value. The probability of being more extreme than the sample value. So for example, if we have a HA where mu is greater than mu naught, then the p-value is the probability of landing or having a data value of having your X bar fall in this region. This is your actual X bar. So what is the probability of having an X bar that's even more extreme than the X bar that you got? That's the p-value. This is the p-value. And how do we calculate the p-value? Well, you have to use sigma to do that. Okay, because you have to calculate your z-score, or your calculator will compute the z-scores. And how's your calculator compute the z-score? Takes your data value, subtracts the mean, and then divides by what?
The sigma.
So the standard deviation, x, z equals x bar minus the assumed mean over the standard deviation of the sample, which involves sigma. Well, if I don't know sigma, how do I compute that?
Do you replace the sigma with something else?
Yes, so
With the sample?
yes, so when you don't know sigma, when you don't know sigma, T equals x bar minus mu naught over S over the square root of n. Technically, these are my Z stars and my T stars, which is just the symbol that we use in this context. When you don't know sigma, you just use S instead. Of course, to calculate the value from the tables, you also need to know the degrees of freedom. And just like the last time, the degrees of freedom is just n minus 1. That hasn't changed. As far as what you do on your end, there's really no difference, because the calculator does all the work for you. You don't really care, do I know sigma? Do I not know sigma? It doesn't make a difference. Whatever you know, you put into the calculator and it will do your work. So let's just demonstrate that by doing an example. Just like we did it for the confidence interval, let's go to the book and just pick an example. So let's apply our knowledge. So, ooh, the sounds tall. She sounds tall. Is this a follow-up of the last one we did? 20.7. 20.7, I think it is. Do the data of exercise 20.7 would give reason to think that the mean number of correct identifications? Okay, so let's do it. Let's think about it. This is a follow-up of the last example. Okay, we have 24 people, and this is the percent that everyone got correct. And the question is there enough evidence to make the claim that people are more likely than not to be able to determine who is taller just by listening to the voice? Now, if they were not able to do this, then what percent correct should people get on average? Okay, if you're listening to 100 pairs and picking out the taller one from the sounds, and you had no ability whatsoever to do it, and it's pure guesswork, then what percent on average should people get correct? Couple chats, people said 50%, right? If you have no reason to think otherwise, then the status quo should be 50%. So the null hypothesis is that the true value, the true number of correct, should be equal to 50. And what are we testing against? We're testing to see if the true value is what? What's the alternative in this example? Anyone?
You said that the hypothesis was equal to 50?
Well, it's not that the hypothesis was equal to 50. Let's think about it. If we think, we as scientists come in and think that people have this ability to determine height from sound. If it's not true, if we don't have that ability, then it's pure guesswork, right? It's pure guesswork. And if it's pure guesswork, then it should be 50-50, like a coin toss, right? We should be right half the time and wrong half the time. But we think that people do have this ability, in which case the true amount, as Mary said, should be greater than 50, right? That's what we're testing here. And that, what do you mean by that?
Like it should be more than 50.
That's more than 50 is correct, right? H naught, the true value, whatever it is 50. And we're testing versus the alternative that is actually greater than 50. Now the question is, how do we test this? Well, 1 second, before we even do that, just for a second, I want to go back to what we did with the confidence interval. Now this is very important. Based on our confidence interval, somebody tell me whether or not we should reject or not reject the null hypothesis. We're not using a hypothesis test. We're using a confidence interval, but we can still get a conclusion about whether or not we would reject or not reject the null hypothesis. What is your conclusion here and why?
I think we should reject the null hypothesis because nothing is less than 50. Everything's above 59.
Beautiful. 50, the value that the null hypothesis claims is the true value, does not appear in your confidence interval. Since the entire confidence interval is above 50%, we're 95% confident that the true value is somewhere above 50%, in which case it's not 50. Okay, so we are going to reject the null hypothesis. If there was any overlap, if it was 49 to 62, for example, even though the majority of the points are over 50, we can't reject the null hypothesis because all we can say is it's somewhere in that interval. And it's just as likely to be on the 49 edge as it is to be on the 62 edge. So you can only conclude something if the entire interval misses your value. In this case, the entire interval is more than 50. And as such, because the entire interval is more than 50, we can reject the null hypothesis by using a confidence interval. Let's also take a look at what happens when I use a hypothesis test. So first, what is the mean under the hypothesis test? What is the null hypothesis claiming is the true value in this case?
50.
50. Is it a one-sided? Is it a less than, greater than, or two-sided case?
Greater than?
It's a greater than. And when we calculate, we get the following situation. Null hypothesis, it's 50. Alternative, it's greater than 50. Notice that the sample mean, standard error, degrees of freedom, those are all the same. Look at the p-value. What is that p-value? And that p-value is so small that all the computer is saying is it's somewhere less than 0.0001. Is that a p-value that would make us reject the null hypothesis? And the answer, remember, is yes, because what's the cutoff? In the absence of anything else, and by the way, we don't have any absence here because they said 95%. But in general, what's usually the cutoff? A p-value less than 0.05. Right, Hannah? 0.05, excellent. So this p-value is so much less than 0.05. I mean, it's so small, even at 0.01, even at 0.0001, we would reject the null hypothesis. In other words, No statistician in their right mind would ever claim that the null hypothesis is, again, we don't accept anything, but we're not reject. I mean, we would certainly reject the null hypothesis here. The data certainly supports it. And by the way, this T statistic, 10.27, let's see how they got that. I claim it's exactly that formula that I gave you. X bar minus the assumed mean under the null hypothesis divided by S over the square root of n. Now, S over the square root of n already is the standard error. That is the standard error. So 62.17 minus 50 divided by 1.185 gives me, on my calculator, 10.27. In other words, the same essential formula as Z, but we just use the letter T because we don't know sigma, and we get an extremely high test statistic. Remember what 10.27 means. 10.27 standard deviations above the mean. Where on my graph would that be if I'm 10.2 standard deviations above the mean? I mean, one deviation is about 68%, two deviations is about 95%, three deviations is 99.7%. I am more than 10 deviations out. That is so negligible of a result that you have to start wondering, is the mean really here when I got a result out here? Or is it more likely that I was way off and it's really over here somewhere? I have to reject this. It's just, I'm so far from there. This can't be right, but this is probably more accurate. That's a thought process behind this, these hypothesis tests. Does that make sense? Yes, everyone? Questions? Anyone have a question on what we did? Of course, let's just do it in the calculator as well. So let's go to second, let's go to stat tests. Which tests are we going to use here? Which test do we use here?
Is it the T interval?
This isn't an interval anymore. This is now a test.
Oh, T test.
Our T test. Data or stats? What do we put in for everything?
We're doing T test, right?
This is a T test, yeah. Put in all your info. And what do we get? Hopefully, you got the same thing I did, which is an extremely small p-value, 10 to the negative 10 power. 5 point whatever, 2 point whatever, I can't read backwards, but an extremely small p-value. Okay.
I have a question.
Yeah.
It might be a stupid question, but how do we know that it's asking for like a greater than or less than, like when
This-
you're reading the problem?
So this if you read the question carefully, let's go back to the question. It said, do the data give good reason to think that the mean number of correct identifications in the proportion of young adults in the United States is greater than 50?
Okay, so it'll always say like in the problem
No.
what we're looking.
No, it will not always say the problem. So sometimes you have to use common sense.
Okay.
And sense is only common if you work at it. So I don't mean like, you can just read it one time and get it. You do have to think about it sometimes. But
Okay.
at the end of the day, if you read the question carefully and you think about it, there should be enough information to ascertain whether it's less than, greater than, or not equal to. And I will tell you that there are times when I read questions in books that even I'm not sure. It's like, it's just the way it's phrased, it's not really clear. And then I think about it a little more and I'm like, oh, okay, no, it has to be this way. Like I think about it and I figure it out. And other times they just straight up tell you.
Okay.
And by the way, they also tell you here in the problem that the expected number is 50 just by guessing. In other words, not only do they tell you it's greater than, but they also tell you what it would be under the null hypothesis where we don't have this property hold. Okay. Anyways, section 25, 20.5. I don't think we're going to do it. Seems kind of silly. I think it just basically talks about how to find these things with various technology. For example, a TI, we did that. Crunch it, we did that. They also give you Excel, Minitab, and JMP. You could also probably go online and just do a Google search for confidence interval calculator or a hypothesis test calculator and find a dozen sites and say, oh yeah, just plug in these numbers and get the right thing out. The fact of the matter is you only need one of them. And if you have one, like the calculator, you're good to go. Your final will be live. You're not going to have access to your computer for your final. So you certainly want to know how to do these on the calculator because you will be expected to do them on your calculator on the final. Meanwhile, section 20.6, the matched pairs T procedure. Matched pairs. So we've done a situation so far, two confidence intervals, one where you know sigma, one where you don't, and two hypothesis test situations, one where you know sigma, one where you don't. There is a special situation called the matched pairs t-test. The matched pairs t-test. Okay. And it is a specific situation that only holds when you have matched pairs. Well, what does that mean? So let me explain the following situation. Suppose I was curious whether or not people can do something more efficiently with their right hand or their left hand. So for example, swing a hammer, okay? Are people better with their right hand or with their left hand at swinging a hammer? I put a nail and I want to see how many shots it takes before the nail, I don't know, I make something up. So which of these two situations would be a better experiment? Getting 100 people to do it with their right hand and getting 100 people somewhere out there to do it with their left hand and then comparing the results, or having the same 100 people do it with their right hand and also doing it with their left hand. Which of those two would give a better portrayal of the difference between right and left hand? So it's the same 100 people, right? Cynthia's got it, the same 100 people, because if you get different people out there, then you're adding a layer of randomness to the situation, of uncontrol in the situation, where maybe they're left-handed versus right-handed, and you're having some additional complications that will be avoided when you compare the same people right and left. Matched pairs are when you have two results per individual, but you match up the results, the same person right and left, the same husband and wife pair, the same this and that, versus two completely different samples. Okay, that one situation is called the matched pair procedure, the matched pair t-test, the matched pair situation. How do we do the test? It's very simple. Step one, compute the differences. In other words, if you have, if you have your x1, x2, x3 up to xn, and your y1, y2, y3 up to yn, I don't look at the x1s or the x's and the y's. What I look at is x1 minus y1, x2 minus y2, up until xn minus xn. That's what I care about. And then with these numbers, do a regular t-test. We call this D1, the first difference, the second difference, up until the nth difference. So when it comes to the match pair t-test, you are just taking the pairs, which are matched up, computing the differences between them. This gives you now a good old single sample with n results. And then do a good old-fashioned regular t-test with the results. So let's do an example of that from the book. Can I close the, can I go share the screen? Anyone still writing this? Okay, so let's do an example of a matched pair t-test. Okay, so I want to do one, which is okay. Apply your knowledge. Okay, 20.11, eye grease. Gross. Athletes performing in bright sunlight often smear black eye grease under their eyes to reduce glare. Does eye grease work? In one study, 16 student subjects took a test of sensitivity to contrast after 3 hours facing into bright sun, both with and without eye grease. So the same 16 people did it with and without. We're pairing up the data. Greater sensitivity to contrast improves vision, and glare reduces sensitivity to contrast. So this thing, sensitivity to contrast, essentially the more glare, the lower that is. So this is a matched pairs design because the same people are before and after. They've already for us calculated the differences with eye grease minus without eye grease, with minus without. And we have the results here, 1, 2, 3, 4, 5, we have 16 data points. And we want to know whether eye grease increases sensitivity to contrast on the average. So we're going to do both a confidence interval, and we're also going to do a hypothesis test. Let's do the confidence interval first. First, here are all my differences. Notice the columns even labeled by differences. Some of these are positive, some of these are negative. Does that seem reasonable when you're having a subtraction problem with data? Sometimes bigger minus smaller, sometimes smaller minus bigger. It is the way it is. If we do a T, and by the way, on this list, it's just a regular T1 sample. Because remember, once you've computed the differences, it's just a regular t-test. So differences. Now, the question is, what is the, first we're in confidence interval. First confidence interval, and I believe the book said 95%, right? Yeah, 95% confidence interval. We can get rid of that one. Okay, so let's calculate it. Okay, so let's compute this, or let's interpret this. First, n equals 16. Do we agree 16 data points? Okay, sample mean and the standard error. We can't agree with them. I mean, they're calculations, but let's assume that they're true and the computer did it correctly. How do I do this in a graph? We'll do it in a second. We're going to crunch it first, and then we'll do it on the calculator. Although if you're going to do it on the calculator, yeah, that's fine. We'll do it both ways. Okay. Degrees of freedom, 15. Do we agree with that? Right, n minus 1, 16 data points, so n minus 1, 15. And then they went ahead and they computed the confidence interval, and they got this. Which number in particular is inside of that confidence interval? Obviously, lots of numbers are, but there's one number in particular that matters that it's in there? What number out of all numbers in the world is in that confidence interval that has special significance for this problem?
The sample,
0.
0.
0. Because remember, we want to see if there's a difference. If there's no difference, then on the average, what should the differences average out to be? 0, right? If there's really no difference, then the difference should be 0. So because 0 is inside of this confidence interval, would I reject or not reject the null hypothesis? The null hypothesis being that there's no difference, and the alternative being either greater than, less than, or not equal to. We'll have to read the question. But certainly the null hypothesis is that there's no difference. Can I reject the null hypothesis based upon this confidence interval? Anyone? Am I allowed to reject the null hypothesis? I mean, not am I allowed? That's bad terminology. Should I reject the null hypothesis? Cynthia, why not?
Because if there's a 0, then that means that there was no difference.
Well, I can't say there was no difference. But if 0's in there, then
We can
0.
assume
Sorry?
and like assume, not say for sure, but like, you know.
Well, there's no reason. Let's try it like this. Any number in that confidence interval is a viable value for the difference. So because 0's in the confidence interval, the data says it could be 0. If the data says it could be 0, why would you reject the null hypothesis? Right? We're using the data to get an answer. The data says it might be 0. Oh, okay, well then it's not 0. That's foolish. Right? If 0's in there and 0's a possibility, and the null hypothesis says it's 0, we have no reason to say the null hypothesis is wrong. And therefore we cannot reject it. Does that make sense? Everyone who's listening, does that make sense?
Yes.
Okay, now if I go back to the question, we just did this one. This is an old one. I don't need this one anymore. If I go back to the question, what are we looking for? We want to know whether eye grease increases sensitivity. So we are looking to see if sensitivity goes up with eye grease. And the difference is with eye grease minus without eye grease. So if with eye grease it went up, would we have a positive number or a negative number under the alternative hypothesis?
Positive.
Positive. As such, when we do a hypothesis test, which side is it going to be? Greater than, less than, or equal to? Or not, or two-sided?
Is it greater than?
Greater than. We want to see if it went up. And 0 is what we're assuming, right? If it didn't go up, if it's just made no difference, then it should be 0. And if we calculate it, what do we get as our p-value? What's our p-value there? 0.047, which is less than 0.05. And this gives us one of the drawbacks of using two different methods, the confidence interval approach and the hypothesis test approach, is that while 99% of the time they agree, there are some situations where they are in conflict. The confidence interval says, do not reject the null hypothesis. And the hypothesis test situation says it's small enough that we do reject the null hypothesis. That will happen sometimes. You will not be given a question on any test where you get two different conclusions based upon what you do. And the reasons why you get two different conclusions are a little deep and we're not going to go into, but it does happen. And this is an example where it happens. It's hard to predict when it happens in advance, but we do get that prediction sometimes that one way we get one result and another way we get a completely different result. But again, the confidence interval approach says do not reject because 0 is in there, although it's barely in there. And the t-statistic approach says we do reject because the p-value is too small, although again, it's barely too small. So when you're really close to that border, there are times that the conclusions are a little bit different. Now, on your calculator as promised, let's go to stats, tests, and again, we're going to do the t-test. What is the assumed mean for the t-test?
0.
It is 0. What is the X bar?
0.1013.
0.1013. What is, sorry?
Did you put the whole thing or could you just go 0.10?
I try to be as accurate as possible. So I put in as many decibels as I know. What is S going to be?
Is it 0.05658 times the square root of 16?
Yes, that's exactly what it is. 0.05658 times 4, which is the square root of 16. And what did your calculator give you for the p-value?
I got 0.046.
Which is what they have there. And by the way, let me tell you why the confidence interval approach and the alternate and the null hypothesis approach, the hypothesis test approach are in slight disagreement over this. And this is a kind of an important fact. The hypothesis test was one-sided, greater than 0. The confidence interval was not one-sided though, was it? The confidence interval goes in both directions, right? If it's a two-sided test, two-sided tests always agree with confidence intervals because they're designed to go both ways, just like a confidence interval goes both ways. One-sided tests only go one way, confidence interval goes both ways. There are times that you get different results. So for a two-sided test, you'll always get agreement with the confidence interval. With one-sided tests, sometimes you'll get a different result. But did I answer your question about how to use the calculator for this, Cynthia? Okay.
If we don't, if we don't have the computer, how would we find the standard error on the calculator?
You could, instead of doing it with stats, you put it with data. And you put all your data points in and have your calculator computed for you.
Okay.
But one way or the other, the calculator is going to be doing something. Does that make sense?
Yes, thank you.
Okay, so that takes care of the matched pair procedure. And all that's left then is the last pair, the last section, which is section 20.7 on the robustness the robustness of T procedures. The robustness of T procedures. So a confidence interval or hypothesis test is robust. If the confidence level or p-value, depending on which one you're doing, the confidence level or p-value does not change very much, when the conditions for its use are violated. So remember, when are you allowed to use these things? Oh, it has to be an SRS. Oh, it has to come from a normal distribution. It has to be this. It has to be this. Well, what if it's not? What if it's not? What if I miss this? What if I don't have this? Okay, so a situation, a confidence interval or hypothesis test is robust if it can withstand these deviations from idealness. So we have a few corollaries to this, a few kind of follow-ups. Case one, what if the sample size is less than 15? If the sample size is less than 15, now remember, this data does not have to be normal, but if the sample size is large enough, it's going to look normal, correct? That was a central limit theorem. We did the applet a few times, right? The distribution can be very strange, but if the sample size is large enough, it will eventually have a normal looking sample distribution. And we know that one of the conditions for these tests is to have a sample distribution that looks normal. So what if it's so small that we have to worry about it being normal? So if n is less than 15, only use these t-tests. Only use these t-tests if the data is close to being normal. What does it mean, close to being normal? Normal, it has to be symmetric, single peaked, and no outliers. If n is greater than or equal to 15, if the sample size is at least 15, then use these t-tests unless there are outliers or strong skewness. And if n is, let's say, greater than or equal to 40, go ahead and use any test you want, any t-test. If n is greater than or equal to 40, then we can withstand any of these violations. On tests, you will not really be given, I don't think you'll ever be given situations on tests where you have to worry about tests not being allowed to be used. Unless the question specifically says, under what conditions can you use the t-tests? That's when these conditions play a role. But if you're just given data and you're said, okay, make an inference, you can just go ahead and assume everything's okay. Okay, but in general, if the sample size is greater than or equal to 40, any test is fine. And I've seen some books even use 30 for this. So there's no hard and fast rule. If it's 15 or more, you can use it unless there's outliers or strong skewness. It's only when n is less than 15 that you really need to be worried. Okay, but as long as it's close to normal, symmetric, single peaked and no outliers, you'll be okay. That's the robustness of the T procedures, that they don't really require normality as long as these conditions hold. Okay, makes sense? Questions on what we did today? Well, then in that case, I'm going to stop recording.